Welcome to G Fun Facts Online. Today, we're journeying into a future that isn't science fiction anymore. Imagine microscopic submarines, smaller than a grain of salt, navigating the 100,000-kilometer highway system inside your body, your veins and arteries. Their mission: hunt down a blood clot, deliver a cancer-killing payload directly to a tumor, or perform surgery on a scale we've only dreamed of. This is the world of medical microrobotics, and it's poised to change everything. For decades, our approach to diseases deep inside the body has been a bit like carpet bombing. Systemic drugs, like chemotherapy, flood the entire body, causing immense collateral damage to healthy cells just to reach their target. Even our more advanced tools, like catheters, are still too large and clumsy to reach the most delicate and distant parts of our circulatory system. But what if we could send in a tiny, untethered agent, guided by an invisible hand, to perform a precise surgical strike? That's exactly what magnet-powered microrobots promise to do. So, how do you control a microscopic object deep inside a living person without any wires? Several ideas have been tried, like using light or ultrasound, but magnetic control, or magnetic actuation, has emerged as the clear winner for navigating our blood vessels. The reason is a combination of physics and biology. The core principle is beautifully simple. Materials that are magnetic experience a force when you put them in a magnetic field. By generating and carefully manipulating magnetic fields outside the body, engineers can exert precise control over a microrobot that has a magnetic component inside it. It's like having an invisible hand that can reach anywhere. This approach has three huge advantages. First is penetration. Low-frequency magnetic fields pass right through skin, muscle, and bone, with virtually no loss of strength. This means a magnet outside the body can control a robot just as effectively, whether it's in a major artery near your skin or a tiny capillary deep inside your brain. Second is safety. The magnetic fields used are non-ionizing and, at the strengths required, have no known harmful effects on the body. This is a critical non-negotiable for anything we put inside ourselves. This also means they can be designed to work alongside MRI machines, potentially allowing doctors to steer and see the robot using the same system. Third, and most importantly, is freedom. Being wireless, these microrobots are truly independent. They aren't held back by the physical limits of a wire or a catheter. This freedom gives them access to previously unreachable parts of the body, opening up a whole new frontier for medicine. But what are these vessel voyagers actually made of? Creating a machine that can survive and function in the bloodstream is a masterclass in engineering. It needs to be tiny, powerful, biocompatible, and functional. These robots are typically composites. The engine is the magnetic material. This can be a hard magnet, like a tiny piece of a neodymium alloy, which is permanently magnetic and very strong. Or it can be a soft magnetic material, like iron oxide nanoparticles, which only become magnetic when an external field is applied. Iron oxide is a popular choice because it's already proven to be biocompatible in other medical uses. The body of the robot is made from non-magnetic materials like polymers or hydrogels. These provide structure and can be designed to be biocompatible or even biodegradable, so the robot simply dissolves safely after its mission is complete. Some are even built with metals like tantalum, which shows up clearly on X-rays, allowing doctors to track the robot's journey in real time. Manufacturing these intricate machines is another challenge, solved by borrowing techniques from the semiconductor industry. Advanced 3D printing methods, like two-photon polymerization, can create incredibly complex, high-resolution shapes. Think of a perfect, microscopic corkscrew. Other methods use templates to deposit layers of material, building the robot one layer at a time. There's even a process called self-assembly, where chemical forces encourage individual components to spontaneously build themselves into the desired structure, just like in nature. There's no one-size-fits-all design. The robot's shape is directly tied to its job. The most famous design is the helical swimmer. Inspired by the tales of bacteria like E. coli, these screw-shaped robots are propelled by a rotating magnetic field. As the external field spins, the robot screws itself through the fluid. Reversing the field's rotation makes it swim backward. For navigating arteries with very fast blood flow, swimming in the middle of the stream is inefficient. So another design is the surface roller. These robots are pulled against the vessel wall by the magnetic field and then rolled along the surface, where the blood flow is slower. Other designs mimic an inchworm's crawl, using an oscillating field to create movement. Some of the most innovative designs are biohybrids. Researchers have managed to attach magnetic particles to living bacteria, essentially putting a magnetic guidance system on a biological motor that has been perfected over millions of years of evolution. For simple drug delivery, the design can be a spherical capsule. These are tiny spheres made of a dissolvable gel, loaded with magnetic nanoparticles and the medicine. The capsule is steered to the target, and then another magnetic field can be used to heat up the nanoparticles, melting the gel and releasing the drug exactly where it's needed. Perhaps the most exciting frontier is the use of swarms. Instead of one complex robot, imagine controlling thousands or millions of simpler ones. Like a colony of ants, they can work together to perform tasks no single robot could, like clearing a large blockage. So you have the robot. Now how do you steer it? The control deck for these microrobots consists of large, complex systems of electromagnetic coils or arrays of permanent magnets. The electromagnetic systems use multiple coils arranged around the patient. By precisely controlling the electricity to each coil, operators can generate dynamic magnetic fields that pull the robot or apply a torque to make it spin. An 8-coil system, for instance, can give you the 5 degrees of freedom needed to fully control a robot in 3D space. These systems are incredibly precise, but they can be bulky and generate a lot of heat. The alternative is using powerful permanent magnets, often mounted on robotic arms, that are physically moved and rotated around the patient. These can generate very strong fields without the heat, but their control can be more mechanically complex. And of course, there are hybrid systems that aim for the best of both worlds. Navigating the body is not like driving on a calm lake. The vascular system is a chaotic environment. Blood flows at high speeds, creating powerful drag that can sweep a microscopic object away. To move upstream, a robot can't just swim. It needs to be pulled by a strong magnetic field gradient, a force that drags it toward the area of highest field strength. Using this technique, some systems have achieved speeds of over 20 centimeters per second against the flow. In a bifurcation, where a vessel splits into a fork, the robot has to make a choice. Here, a combination of techniques is used. A magnetic gradient can be strategically aimed along the wall of the correct branch, guiding the robot into the right path as the blood flow tries to carry it straight ahead. Of course, to control the robot, you need to know where it is. This is done with real-time medical imaging like X-ray fluoroscopy, but a single microscopic robot gives off a very weak signal, making it hard to track. Right now, most systems are under direct human control. An operator watches a screen and adjusts the magnetic fields. But the ultimate goal is autonomy. Researchers at institutions like ETH Zurich are using artificial intelligence and reinforcement learning to teach microrobots how to navigate on their own. By training algorithms in virtual simulations of blood vessels, the AI learns the best strategies for moving and avoiding obstacles. In early trials, these AI-powered microrobots have shown remarkable success, pointing to a future of intelligent, autonomous systems that could navigate our bodies with minimal human supervision. The journey is not without its hazards. The force of blood flow is the most formidable obstacle. It can be turbulent, with unpredictable eddies that can pull a robot off course. The vascular network itself is a maze of nearly 100,000 kilometers of vessels that branch, twist, and shrink down to diameters so small that red blood cells have to pass in single file. And, of course, The body sees any foreign object as an invader. The robots must be perfectly biocompatible, not triggering an immune response or causing blood clots. For many uses, they also need to be biodegradable, safely dissolving away after their job is done. Despite these immense challenges, the potential applications are nothing short of revolutionary. This technology could finally deliver the